Hello, we're here to talk about the Manual Wheelchair Efficiency Performance Assessment tool that we've developed as part of the Rehabilitation Engineering and Applied Research Lab at Georgia Tech. My name is Jacob Misch. I'm a postdoctoral researcher at the Rear Lab, and I'm joined by my colleague Yogesh, who is the research engineer at the Rear Lab. The problem that we've come here to talk about is that manual wheelchairs are inherently difficult to propel. In terms of gross mechanical efficiency, a unit that's used to compare different modes of transportation, manual wheelchairs ranging from standard to the high-performance ultra-lightweight wheelchairs only get about 3 to 7% gross mechanical efficiency, which pales in comparison to even walking at 15% or bicycling at 23%. Because of the unique way that manual wheelchair users are required to propel with their upper extremities, the risk of injury to the shoulders and elbows and wrists are high. And with 5.5 million daily users at least, this risk is not insignificant. We've found in previous research that better parts, components, and configurations can improve performance, but this option is locked to less than 1% of users that utilize ultra-lightweight wheelchairs. Our problem statement we've distilled into two claims. More efficient chairs mean lower user energy expenditure, lower forces, and lower risks of injury for the user. And there are currently no performance-based metrics to rate manual wheelchairs objectively. The stakeholders we've defined for this project include anyone associated with designing, setting up, or using manual wheelchairs. Of course, the end user would be the wheelchair users themselves. The decision maker is anyone involved with setting up the initial configuration of the chair, including not only the wheelchair users, but the clinicians, insurance providers, regulatory agencies, manufacturers, and retailers who provide that wheelchair. Influencers include the clinicians, manufacturers, insurance, and regulatory agencies. And the saboteurs we've identified as the manufacturers, insurance providers, and regulatory agencies. Our proposed solution to rating manual wheelchair performance objectively is the AMPS, or the Anatomical Model Propulsion System. The AMPS is a robotic wheelchair tester that can be deployed across virtually any manual wheelchair on the market. Its size and shape mimic that of a human occupant, and its propulsion can be configured and controlled across a wide array of testing environments. The video on the right shows the AMPS in motion. The pushes that it deploys, the pushing and coasting, is very reminiscent of a human occupant or a human user, and it can be configured to go in a straight line or in a slalom or serpentine-like path, or even in a fixed wheel turn or an alternating zero radius turn to reflect different use cases of a manual wheelchair. The AMPS allows us to measure a metric called propulsion cost, which is the ratio of energy input to the system by the AMPS over the distance that the system travels in any given maneuver. This is most analogous to miles per gallon in automobiles, as miles per gallon reflects different mileage on city versus highway driving. Propulsion cost also reflects different use cases, such as going over tile or carpet or sidewalk. Ultimately, propulsion cost boils down to how much energy does a user need to exert to get the chair and themselves from point A to point B. A higher propulsion cost represents a chair that is more inefficient. As a demonstration of the utility of this propulsion cost metric, we devised a study to compare one high-strength lightweight wheelchair as configured by the manufacturer with the default drive wheels and casters equipped to the same chair with a different set of casters and drive wheels that showed much more advanced performance over tile and carpeted surfaces. We found that when we replaced both of these components, we could reduce propulsion cost over tile by 41%. Evidently, this new configuration used much less energy than the default configuration. With all of the energy saved, the user could travel an extra 1.1 kilometers per day. And this is not insignificant considering the average daily travel of a wheelchair user is approximately 1.6 kilometers. The outcome, The moral of this story is that good tires can make significant differences, and these are reflected in component level testing, which is widely used throughout the industry. However, that needs a connection to real-world use. The AMPS can give us that real-world perspective, and the AMPS can rate good versus bad configurations, wheelchairs, and/or components. There are several clear benefits to our stakeholders. For one, wheelchair users and clinicians can now use results about performance to make informed choices when deciding between their preferences and monetary cost when setting up their next wheelchair or their first wheelchair. The benefit to manufacturers is that we've identified which features make wheelchairs more efficient and better. To regulators, they can now optimize the available options and look at all these different categories of wheelchair to make sure there are good, efficient wheelchairs available to those who need them. And to insurance providers, the main benefit is that they may be able to cut their long-term health costs by promoting this idea that better wheelchair performance may lead to reduced risk of injury because you're using less energy for propulsion. To define our primary competition, we first asked the question of how are manual wheelchairs currently compared? Regulatory agencies use three comparisons: frame weight, weight capacity, and configurability to define at least 5 different wheelchair classifications ranging from standard to ultra-lightweight wheelchairs. And these classifications heavily influence the pricing and the prescription of these wheelchairs as seen by the prices on the left. Anywhere from a standard to a lightweight can cost up to $600, whereas most ultra-lightweight wheelchairs don't even start until $1,000. There's heavily implied to be performance differences between these categories, but regulatory agencies use no performance metric to distinguish between these groups. And so these classifications are currently based on these archaic definitions of what makes a wheelchair good or bad. We then looked at wheelchair testers who use comparisons of durability or human metabolic cost or even rolling resistance of the components to perform different evaluations based on the mechanical performance of the system in realistic or simulated environments. However, these mechanical measurements are often subjective or lack comparability or lack that real-world relevance that the AMPS can give us by propelling over real-world environments at real-world speeds. So the differentiators that we've identified for this project is that our solution, the AMPS and propulsion cost, they are scalable, they're repeatable, and they fully reflect real-world usage over multiple environments. The controllable testing aspect we've condensed down to the slogan of any maneuver, any chair, anywhere. We've also removed biomechanics from the system so that we have a perfect test subject whose weight distribution, and propulsion characteristics never vary. And it's a relevant metric that we produced with the propulsion cost. Use 40% less energy per day sounds as good to a wheelchair user as it does to a manufacturer, as it does to a clinician. We've developed an action plan to disseminate the information we've learned from the AMPS and propulsion cost data towards the clinicians and wheelchair users where it'll be the most beneficial. We're in the process right now of finishing up 2 ongoing studies, and we'll prepare these studies for publication in peer-reviewed journals. We also plan to make this information available online in a user-friendly format where anyone can look up their components and see how well they stack up against the competition. Over the following few months, we will be connecting with clinicians, manufacturers, and wheelchair users to identify future topics to investigate with the AMPS. Finally, we'd like to further develop the AMPS for use as a testing service for manufacturers to objectively rate their components. As an ultimate goal, we would like to compile these findings and present them to policymakers to advocate for better prescription practices and to raise awareness about the necessity of wheelchair performance testing. Thank you for listening, and we hope that you reach out and contact us if you have any questions or comments using any of the links below.